All right, our next presenter, leading us just out of winter and talking about St. Vincent and the Grenadines in the Caribbean, is Jacob Gaskill and Brian Zuber. And Brian Zuber is not in attendance today, so take it away.
So, as he said, my name is Jacob Gaskill. I'm going to talk to you a little bit about our modeling landslide risk in St. Vincent and the Grenadines. So, I really like this picture because this is not a landslide. But it's taken in St. Vincent and the Grenadines. You can see that the road is cut into the mountain. That slope is perpendicular with the road. Many of the roads in St. Vincent and the Grenadines are like this. So you can see there's a little bit of debris on the actual road. You can imagine what the road would look like if an actual landslide happened. It'd be pretty substantial. So when we talk about measuring natural disaster risk, we're talking about three factors. Basically, what are the spatial factors that cause, in this case, the landslide to happen? Who is the natural disaster affecting? So when we talk about infrastructure, we talk about where population is densest. And then exposure references the temporal factors. So if there's a landslide that requires a couple inches of rain, that triggering event, that temporal factor, is going to be much more frequent and increase the risk than if that landslide required 10 or 12 inches of rain. So here we look at a couple spatial data sets, so that's why we're focusing on susceptibility. This isn't a true risk model. Unfortunately, there's not a lot of data that's available in this area of the world that we can actually use that's consistent and continuous enough to be of use to us. So we focused on slope and aspect as our two spatial data sets. You can see here, this is the country of St. Vincent and the Grenadines. Our analysis focuses on the main island of St. Vincent. There's a volcano in the northern part of the island. It has over 1,100 meters is the highest elevation. So it's a relatively small island. You can imagine the great change in elevation that happens and how steep some of the slopes might be on the island. So in terms of St. Vincent, what are some of the things that are most affected? Farming is the second biggest economic industry on the island. Most of the farming is small scale, so it'll be one individual farmer or a farming family. So you can imagine that if that family only has a couple of fields and one of them is wiped out completely by a landslide, that's a substantial hit to their income. And then this figure doesn't take into account the time it takes for a banana tree or a coconut tree to grow to the point where it produces fruit. For a banana tree, that could be as long as a year. For a coconut tree, 12 years. So in terms of the government, electricity generation and water transportation is another big issue. I put them together because a lot of the electricity on St. Vincent is generated by hydroelectric power. So when a landslide wipes out water pipes, it leaves a substantial percentage of the population without water, without potable drinking water, and without electricity. And then one of the biggest expenses in St. Vincent for clearing landslides is roads. You can see this picture here, this road is so damaged that it might have to be completely scrapped and they might have to build a new road. The road network on St. Vincent is not extremely expansive, so when a major road is disrupted, it becomes a pretty high priority to try to fix it. Finally, many buildings aren't regulated. Here you can see maybe 50 or 60 years ago this would have been a great place to build. You're right next to the coast, but it's not looking in a great shape now. The building's abandoned. It's probably going to collapse pretty soon. And as many as 40 to 60% of the buildings on the island aren't regulated. So that's a mechanism that government does not have to try to mitigate the effects of landslides on St. Vincent. So I mentioned earlier the slopes on St. Vincent are very steep. The soils are very shallow. It's relatively young from a geologic perspective. The island was formed when two plates converged and magma came up to the surface and solidified. So there hasn't been a lot of time for the bedrock to erode and create a deep soil layer. If you combine these two factors with Agriculture. So you can see here, this is a coconut plantation. There aren't a lot of roots holding that soil together. And if you combine that with what the native vegetation would look like, it would be all covered. It would have a much more expansive root network to hold the soil together. So those factors really cause landslides. And then, as I mentioned earlier, precipitation. So tropical storms are common in this area of the world. Hurricanes are not uncommon. So when we started our analysis, the last formal assessment of landslide events on the island was in 1988. We were fortunate enough to get into contact with the person that headed up that assessment. So we got PDF files of the actual maps created in 1988. You can see that the red dots here are where landslides actually occurred. The red triangles are how the landslides were measured. Mr. Jerome de Graaf and his team flew over the island in helicopters, and they looked at areas of Earth that were exposed. And then you can see that this infrared image, it's a little hard to tell, but if you see there's gray right here, there's a little bit of gray around there. This is a relatively recent image, and you can still see Earth exposed. So even 10 to 20 years later, you can still see the effects of some of these landslides. So we digitized the landslide events on the PDF, and we came up with a total data set of 463 historical landslides. After we got this historical landslide data set, we ran logistic regression on our model. So remember, we started off with two independent variables at first. One was slope and one was aspect. And logistic regression is a great modeling technique for landslides because the dependent variable is binary. So a landslide either happened or it didn't happen. Most other modeling techniques require the dependent variable to be continuous. So logistic regression is used all around the world to model landslides because it does so well with categorical binary data. Also, it's good for medium scales. There's no global model for landslides because there's so many different factors that influence if the landslide is likely to occur or not. So when we look at this medium scale, logistic regression is great. So as I said earlier, we looked at slope and aspect. We ran our regression model twice. After the first time, aspect was not significant. So we ran it again. Slope was significant. And you can see this is our R-squared value. So this value explains the amount of variation in between the landslide events. And it's not that high, right? So our model explains almost 18% of the variation between landslide occurrences on the island. Keep in mind that we only have one independent variable. So we're only looking at slope. So slope explains about 18% of variations on St. Vincent for landslides. It's not great, but at the same time, with the limited data, we were pretty happy to see that one variable explained such a high percent of the variation. We're working with right now, we have a spatial bedrock data set and a land cover data set that we're working with. So we're hoping when we add these data sets into the model that R-square value will go up, that the predictive power of our model increases. So after logistic regression, we ran our Co-Kriging analysis. Co-Kriging is great. It's based off of Tobler's first law of geography. So points that are near to each other will be more similar than points that are far apart. Before we can run Co-Kriging, we have to test for spatial autocorrelation, and we do that using Moran's eye, one of the spatial statistical tools in GIS. So Moran's eye gives us two outputs. First of all, is the data set you're using significant? Slope was significant, aspect was not, so that's consistent with our logistic regression model. And then it also gives you a coefficient. So any coefficient that's greater than 0.3 or lower than negative 0.3, the farther away from 0 we are, the more spatially autocorrelated they are. 0.3 is kind of a general rule of thumb cutoff. If it's more than 0.3 or less than negative 0.3, we can kind of start to say that there's substantial autocorrelation. So slope is substantially autocorrelated. So that's good. We were happy with that. This is one of the outputs. This is our covariance plot for Co-Kriging. Covariance is on the y-axis here. It's an index for similarity. And then distance is on the x-axis. And remember Tobler's first law. You look when distance is small, similarity is very high. When distance is high, similarity is pretty low. So this is exactly what we would expect our covariance plot to look like. If it was more horizontal, that might raise some red flags, but it's not. So it kind of lends confidence to our Co-Kriging model. So this is our Co-Kriging analysis. The model here is the same on both of these maps. The difference between the maps is the information that's overlaid. We were able to obtain land cover data, and we classified densely urban areas. So on the graph on the right, that is, it was a fairly coarse data set, so we don't feel confident at this time about quantifying these areas yet. However, that's kind of our next step. We're working to try to refine the data set now. And then on the right here, all these red dots indicate where the landslides actually occurred. So that's our historical landslide data set. And it makes sense every time that a red landslide is matched up with the red Co-Kriging model. The model predicts where landslides are more likely to occur, so we would want our landslides to be in the red areas, the likely areas on the model. You can see that there are a few areas, or are a few landslides that don't seem to be consistent with the model, but for the most part, the actual landslide events line up with the model. We looked at this more in depth with a validation analysis. So we had our 463 historical data set. We created 400 random points and combined these. So we had 863 total points. Of those total points, we set aside 198 as validation points, and we compared what those validation points were. So remember, they're a mix of actual landslides and random points. And then we compared those points with what our model suggested would be presented. 82% of the time, our model was accurate. In the literature, it seems about 75 to 80% accuracy is good, so we were happy with our 82% accuracy. This kind of validated the model to us. It showed that the information it was presenting is fairly sound. With that being said, it's really important to note this inherent error with these GIS-based statistical approaches. They're based on the idea that will cause future landslides to occur. And if you look at these real landslides in Canada and Italy, obviously where the landslide happened is a lot different than the surrounding mountainsides. So inherently, this assumption is wrong, right? Slope gets changed pretty dramatically, land cover gets changed, the topography gets changed. So it's important to keep that in mind when we use this modeling technique. With that being said, these statistical models, like logistic regression, like Co-Kriging, seem to be the most effective predictors of future landslides and the best way to model landslides that have already happened. Many studies are out there comparing traditional landslide evaluation models. So someone will go out in the field, an expert, and based on several different parameters, they will predict whether a landslide happened or not. And then that expert's opinion will be combined with a logistic regression model. And more times than not, the logistic regression model is just as accurate or more accurate. So, as I mentioned before, we had a limited amount of data that was available to us. So we had slope and aspect data, spatial data available to us. We think our logistic regression model would be strengthened a lot if there was more data. So based on the literature in other areas of the world, proximity to the road seems like it would be very useful to have. So you think about when you're building a road through these steep mountain slopes, you're exposing a lot of the bedrock to erosion and to weathering. If you remember that opening picture I showed you, that road cut right through that mountain, and you saw the whole mountain was exposed to weathering. Furthermore, they weaken the bedrock that's already there. We also think that stream power index would be good to have. The stream power index is an indication of a stream's erosive ability. A lot of the streams on St. Vincent are narrow. They're very channelized because the slopes are so steep. So I would imagine that the stream power index would be fairly high. And then finally, lithology and bedrock data. We are in the process of trying to procure some of that right now. across the globe, slope and lithology data seem to be the two best predictors for future landslides, as well as the two factors that explain the most variation between landslides. So I'm really interested in seeing if we can get our hands on that. As I mentioned earlier, precipitation, it is high in this area of the world. And precipitation is a triggering event, right? It rains a lot, a landslide is more likely to happen. So if we could have some precipitation data, continuous precipitation data, we would start to get into that temporal factor that is important when we're trying to create a risk model as a whole for landslides. Our biggest thing though is that we really think data has to be standardized and consistent. You know, in the wake of a natural disaster, it's not many people's first priority to go out and collect data for obvious reasons. But without these consistent data sets, it becomes very difficult to do these accurate spatial statistical models. So just to kind of wrap everything up, we were happy with the level of accuracy that our Co-Kriging model had. We were also happy that our Co-Kriging model was fairly consistent with our logistic regression model. Aspect was significant for neither model, while slope was significant. So our biggest takeaway here is that, at least with St. Vincent, slope seems to describe a lot of variation in between landslides. So that, I think, is the biggest takeaway. And we hope that this information will aid in future management decisions. So you can see here, this is taken in St. Vincent. The house is destroyed. Several people were killed in this event. And it's a pretty steep slope right there. So our hope is that with more information available to managers, they'll be able to suggest where areas shouldn't be developed and where they should be developed in the future. So hopefully events like this happen less. So unfortunately, I've never been to St. Vincent and the Grenadines. So I've had to live vicariously through images from the Digital Globe Foundation, Corbis Images, and Dr. Nordman. We would also like to expend a special thank you to Mr. DeGraff. Without that historical landslide data set, we wouldn't have been able to model this stuff. Both of our models were contingent on having that historical landslide data set. And finally, I'd like to thank the other people that worked on this project. A lot of bright young minds, and it was really great bouncing ideas off of each other. And at this point, I would like to open the floor to any questions you might have and receive any comments you have.
Why did you pick this island? Was your professor heavily involved in this region? Is that why you set up in St. Vincent?
Yeah, yes, he was. He's done work there in the past. Also, in the Caribbean, landslides are pretty common. Again, there's not a lot of soil. Heavy rains, triggering events are common. The active volcano here, this island is especially steep. So compared to other islands in the region, St. Vincent the frequency of landslides is fairly high.
So I'm just curious, you said that the most recent available data was from 1988. Was that just the only one that was published, or was there just legitimately no other data?
That's the data that we can get our hands on. One of the biggest issues is that data that is present might be present in one department of the government, but not in another. So if a landslide wipes out a road, the Department of Transportation might have information on that road. If it wipes out a water main, the utility department. So it becomes very difficult to try to combine those data sets into a workable, consistent thing that we feel comfortable with adding into the model. We like the one in 1988 because it was standardized. The same people measured all of those landslides, so we felt comfortable adding it into the model.
Where did the elevation data come from, and what was the source of that?
The elevation data was from the Aster satellite. We got it from the Earth Explorer database.
What resolution? What's the resolution of that?
30, I think.
30 meters. 30.
Yeah.
So what volume of soil has to be displaced before it's considered a landslide? Is there any common set of criteria for that?
I can't give you exact numbers. I know there are there are several different categories, and then within those categories, there's several different types. So technically, you could have a bunch of rocks that fall. That's technically a landslide. You could also have a giant mudslide come through. That's technically a landslide. As to the best of my knowledge, there's no cutoff for officially this is a landslide and officially it's not. It's more we're more interested in the magnitude of the amount of earth that gets moved and the implications that has on people and infrastructure.
And the banana and coconut trees, are those native to the island?
No. So I think British colonization happened in the late 1700s. From that point on, cash crops were grown a lot more frequently. Land was deforested. In this area, bananas are the #1 export and coconuts are the #2 export. A lot of small-scale stuff, a lot of small-scale farmers doing that. They'll have side gardens to feed their family, maybe sell extras at market, but for the most part, a lot of bananas, a lot of coconuts, not native.
So similar to agriculture here or anywhere really, a lot of times the native plants that have developed over time, maybe because they're more adapted to shallower soils, have a better chance at holding the soil together, reducing erosion. Are any of those native plants cash crops that could be grown for profit or edible? Are they even edible?
That's a good question. I don't know a ton about the flora on St. Vincent. I think the biggest thing with the natives that regardless of what's being grown, just the sheer biomass sheer biomass and abundance of plants on the land are holding everything together. As to what can be grown for useful food, like I said, I know farmers have side gardens that they use to feed themselves and their families quite frequently. I don't know how feasible it would be to export crops grown in those side gardens. That answers your question.
Yes, it is. Thank you.
Question about your validation. So you have your set-aside points. The Kriging output is going to be some kind of a value ranging from something like 0 to 1. So how do you decide if it's correct or not?
We set the cutoff 0.5. If it's greater than 0.5, a landslide. If it's less than 0.5, not a landslide.
I gotcha. Okay.
So we were debating. You can kind of see on the scale there. Yellow, so anything orange and above is where a landslide happens.
Okay, so if there was a landslide in one of those locations, you would say you correctly identified it. If there was a landslide in a green value, it would be incorrect.
Yes, exactly. And we're able to see too, does it over-predict areas that are at risk compared to not at risk? I didn't include the table, but it's in the paper.
Yeah.
I have a comment about you said you wanted to work more toward risk modeling. And I heard you saying that the volcano is 11,000 meters? Or
1,100 meters.
1,100 meters, so not all that. Somehow I assumed it was taller. Then I was going to ask you about like microclimates in the area, where you might have areas, especially with prevailing wind directions, potentially during different parts of the year, where you might see differences in precipitation that if you're just taking the average, you might not pick up.
Well, that's the thing too. I didn't get into it because I was a little worried about time, but you can't just use precipitation at the capital at Kingstown because that's very different than up north. And when you're talking about landslides too, the amount of precipitation that might cause one landslide might be different based on other environmental factors. So you would really need to measure precipitation at different locations, at least close to where the landslide happened. Exactly what you said.
Are you working with a organization on the island, or is there funding for it? What is the motivating factor, driving force for this? Personal interest?
It's Dr. Nordman. He's worked there in the past. It's mostly, as far as I know, there's not a lot of work in a lot of these countries modeling this sort of thing, so we're trying to fill the void there.
So, if I may jump in, this was a class project. So in the fall, I had worked with the Pan American Development Foundation on developing a climate change adaptation and disaster risk reduction curriculum for young adults in St. Vincent and the Grenadines. So we use this kind of as a case study, the island and its geography as a case study for the class, the applied station analysis class. And Foundation, the local partners in St. Vincent and Grenadines.
So are you going to do more research? Are you going to develop this?
I hope so, yeah.
And are you looking at this as a repeatable methodology for different islands or
I think so. This is our
areas?
first, this is hot off the presses. The students, just finished this up. They've been working on it for the last couple of weeks, so we're looking to get feedback and make it better. And we really appreciate your comments and suggestions.
It's difficult to create repeatable models. There's a lot of work that tries to model landslides in other areas of the world, India and Japan, but those factors are a lot different than the factors here. So I think it's useful to apply to other areas. Slope consistently seems to be a pretty big explainer of landslides. Bedrock and lithology consistently seems to be a pretty big explainer, but I don't think it's possible to create one model here and apply that model in India and vice versa, if that answers it at all.
I was really wondering about, if you're doing a lot of the work, shouldn't you get to go to the island as well?
Preaching to the choir.
Last question, Chad.
Have you guys thought about integrating like population densities and that kind of information into this? I would think that'd be real valuable for emergency management situations.
Yeah, and especially infrastructure. That's what we're kind of working on now. We have a pretty coarse data set that we use to kind of classify the population densities. If we can kind of try to refine that technique, it really starts to get to the vulnerability part of that risk model and get one step closer to creating a total risk model. But you're exactly right, yeah, it would be great to have that.
All right, great, thanks, Jacob.
Thank you very much.